Hey Sharon, how are you? Can you hear me?
Hello?
Hello, can you hear me?
Yes, I can. Can you hear me?
Yep, I can hear you.
Okay.
What time is it
Yeah,
for you right now?
beautiful. It's 1:34 p.m.
Okay,
in the
that's
afternoon. How about yours?
yeah. Right now it is 7:34 p.m.
Oh, that's very late. I hope that's okay with you though.
Yeah, that's okay. That's okay. Like the
Okay.
link that I sent you to schedule with, like all those times were my availability, so it's okay. Don't worry.
Okay.
Mhm,
All right, sound good then.
mhm. So thank you for sending me this worksheet that you wanted to go over today during the session.
Thank you for your time, actually.
Yeah, no worries. Are you like starting OChem? Like how long are you into the school right now?
I have just started my pharmacy degree, so this is one of the subjects.
Oh, okay. And have you
Yeah.
attempted or tried this worksheet yet?
Um, I have, but I don't know any of these questions. I have not done chem before, especially organic chem.
Okay, yeah. So we could break it down. Right? So the question, let's start with question one over here. They give us two
Sure.
molecules, sacubitril and valsartan. This
Yeah.
question here is asking us to identify all functional groups
Hmm.
in the combination of sacubitril and valsartan, which is used in the
Yeah.
treatment of heart failure. Okay,
Yeah.
so functional groups is a specific arrangement of atoms, right? So some examples that I could give you here are going to be this. So let's say, give you some functional groups here.
Mhm.
Let's start off with the carbonyl land, right? Because there are a lot of carbonyls. A carbonyl is a carbon double bond oxygen, right? That's an umbrella term because there are a lot of them. We can have an aldehyde, right? Where the carbonyl here, which is this carbon double bond oxygen, is in between a hydrogen and an R group. We can have a
Mhm.
ketone where the carbonyl is in between two R groups like that. We can have a carboxylic acid where we have a carbonyl in between a hydroxy group and an R group like that, right? Um,
Um,
we can have an ester, right? Which is a carbonyl in between an OR group and an R group.
sorry. What is the OR group and the R group?
Hmm. Yeah. So an R group is going to be a hydrocarbon chain, like anything with carbons and hydrogens usually. So some examples of that would be like this. Like if I were to give you this ester over here,
Yep.
right? This is the R group, the hydrocarbon chain. So there's a lot of hydrogens and carbons in this group here. And this
Um,
is the OR group here, where we have an O here, and then the R is like hydrocarbon chain. So this chain here has hydrogens and carbons. Right. So
okay.
the R group can be a methyl group, an ethyl group, a propyl group, a butyl group, isopropyl, uh, it could be sec-butyl, like that. Like the R group is
Okay.
any molecule with hydrogens and carbons in it, like that.
Okay.
Right? Nice. Okay. Um, Now that's why I drew R here because it's more general, right? It includes
Mm,
more things. Like we can have different esters. Like that is one type of ester. Another type of ester is this right here, right? It's still the same R and then carbonyl and then OR, right? This
um,
is the R, this is the carbonyl, this is the OR, right?
okay.
This
Yep.
is the R. This is the carbonyl. This is the OR, right? The
Mm.
R could be different. That's why we generalize it to say R,
Okay, yeah, makes
right?
sense.
Mm-hmm. That's
As
good.
long as long as it doesn't have a letter, right? Like a BR at the end of it or anything, we can consider it as R. Is that right?
Yeah. As long as it doesn't have any heteroatom like oxygen,
Yeah,
bromine,
yeah, yeah, yeah.
nitrogen. Right, right. Mm-hmm.
Okay, makes
That's
sense.
good. Yep. In amide, there's going to be different types of amides here, right? But
Mm-hmm.
the most simple one is a carbonyl in between an R group and an NH2, right? Another one would be if the nitrogen is attached to another R group and one hydrogen, or the nitrogen could be attached to two different R groups, like that, right?
Uh,
Where you notice how here all of the nitrogens here are attached to like three things, like they have three bonds, one, two, three, one, two, three, one, two, three,
yeah.
right? Nitrogen with three bonds will be neutral, like that, right?
Uh-huh.
Okay. Um,
Yep.
we can also have something called a nitrile, right? Which is going to be RCN, where there's a triple bond between the C and N, a triple bond between the carbon and nitrogen, like that.
Okay.
Hmm. Yeah. Now, there's also alcohol, right? Alcohol, where it's going to be ROH. So there's going to be actually three different types of alcohols here. You can have a primary alcohol, where if you look at this carbon here that is attached to the alcohol, OH, it's
Mm-hmm.
attached to one other carbon. If you have a
Okay.
secondary alcohol and you look at this carbon here that is attached to this OH, it's attached to two other carbons like that,
Yep.
right? Now, if you have a tertiary alcohol, you're gonna have an OH that is attached to three other carbons like this. One, two, three.
Uh-huh.
Okay.
So basically, if OH is connected to a carbon.
Yeah, that is an
Okay.
alcohol. Correct.
Okay.
Yeah. Now we can also have an ether where it's gonna be an oxygen in between two R groups, right?
Okay.
OR. Okay. We can have a thiol where we have sulfur attached to hydrogen and an R group. So thiol and alcohol, they're very similar, right? Alcohol is ROH, thiol is going to be RSH, right?
Just have the sulfur in the middle, right?
Yeah, sorry.
It just has the sulfur in the middle. That's
Yeah,
the only
yeah. Right,
difference.
right. It has the sulfur in the
Okay.
middle, right?
Okay.
Whereas alcohol has oxygen in the middle,
Okay.
right? And when you see a structure like this with a ring and three double bonds, this is
Yep.
what we call a benzene group, functional
A
group.
benzene.
Yeah, benzene, right. Benzene. Nice. Okay.
Mm.
And if you have RX, right? Where X is fluorine, chlorine, bromine, or iodine, any halogen,
Yep.
we call this either a haloalkane, right? Because it's halogen attached to an alkane,
Yep.
or alkyl halide, like that, right?
Um,
Okay, nice. Um, so now if we go over here, um, just by looking at it, you can take a screenshot of this. How?
oh, yeah. Let me just quickly do that.
Yeah.
A little bit more up, please.
Yeah.
Yeah.
Hmm.
Okay. Beautiful.
Hmm. Yes. Um, I could make boxes here to make it more clear.
Oh, okay, yeah, thanks.
Yeah. Do you also have the answer key to this worksheet so we could check our answer?
Um, I'll have to quickly double check that.
Yeah. Oh, and there's also another one, an amine where you can have like NH3 or
Mm,
RNH2 or R NRH, or you can have three R's attached to the nitrogen. But we notice here that nitrogen will have three bonds to be neutral, like that.
um, so nitrogen and three bonds.
Yep, nitrogen and three bonds, correct.
Okay.
Not next to a
Uh,
carbonyl, because if you have a nitrogen with three bonds like this, right here, next to a
yeah.
carbonyl, it would no longer be an amine, it would be an amide, right?
Okay.
So that's a
Yeah.
subtle difference. And also the
So
same for
that one.
and ether, right? Ester and ether are very similar, but ester has a carbonyl.
Oh, wow. But
Mhm.
the ether only has an oxygen in the middle, right? Is
Yeah,
that the only difference? Okay.
ether has an oxygen in the middle, and ester also has an oxygen right here in the middle, but that oxygen
Mm-hmm.
in the middle is next to a carbonyl as well.
Um,
Mhm. And then the
um,
amine has nitrogen with three bonds, same as the amide, nitrogen with three bonds, but it has a carbonyl nearby.
okay.
Yeah. So you could take a screenshot of this here whenever
Yeah,
you're
I'm gonna take it.
Mhm.
Okay.
Okay. Good.
I'm just gonna see if I can find
Mhm.
answer sheet to double check that as well.
Yeah. And could you also send that to my email as well so I could like break it down for you so I could teach it the way that your
Oh,
teacher wants you to know it as
yeah,
well?
sure. I'm
Thank you.
just gonna, no, I should
Yeah.
have done that earlier. Sorry.
That's okay. Yeah.
Are you a student yourself or you're not
Oh
a
yeah,
student
sorry.
anymore? Are you a
Sorry.
student yourself?
Tutoring myself?
No, are you a student yourself?
Yes, I am a student myself. I'm in
Yeah, what do
chiropractic
you
right
study?
now. I graduated from college, UC Davis already, like in
Yeah.
2024, 2 years ago. So right now I'm in doctorate's program, chiropractor school.
Oh, wow, that's
Mhm.
nice.
Yeah.
Like,
What are you studying right now? What's your major?
I'm doing a bachelor's of pharmacy and master's of pharmacy practice.
A pharmacist.
Yeah, pharm.
Mm-hmm.
I did another bachelor's because I didn't know what I like to do.
Mm-hmm.
And then because I was working at a pharmacy already,
Mm-hmm.
then once I finished that bachelor's, I was like, I'm interested in this. Let me give this a go.
Mm.
Yeah. Um, can you please scroll up a little bit? I want to see if this answer sheet that I have is the same as yours on the screen. And a little bit down. I just want to see the main worksheet that I've sent you. Oh yeah, this one. Question. Oh, I think it could be. Can I see what is question of the last question of the first question, if that makes sense?
Mm-hmm. Last question after the first question. This one?
Yes. Okay, beautiful. I think that is it. I'm just gonna send that.
Okay. Yeah. So this organic chemistry class that you're taking right now is a little bit different than what I learned. So there's some of the things here that I'm not too like confident in, but I could like
Oh,
teach
really?
the stuff that I'm confident in. Yeah. Like I could take
Okay.
the key and then
Is it different though?
a little bit different, a little bit different. Right.
Ah,
Right. Because like the
I'm
percent
just,
ionization values is not really taught in like regular organic chemistry classes. Right. But everything else is
t-
taught the functional groups, pKa. Yeah.
I actually have, I find it difficult to learn the pKa and everything because
Mhm.
I've just never done chemistry.
Yeah, yeah, I can show you
I
that.
don't know how. Okay, thank you.
Mhm.
I've sent it to you. Did you receive it?
Yeah, let me double check here.
Sure.
Um, okay. Yep, I see it. Let me add it to the document and I share my screen again. Okay. Okay. Can you see my screen? Mm-hmm. Okay, that's good. Okay, okay. Yeah. So, what we could do is I could break down the answer key for you, or we could try like working through this by ourselves and then check the key afterwards. Um, Looking at this structure over here and the screenshot that you took earlier with these functional
Yeah.
groups, what functional groups do you see from this molecule here?
I can see two benzene
Mm-hmm.
rings.
Right?
Yeah. Um, Let me see if I can also have that on in front of me.
Mm-hmm.
So two benzene rings. Let's see. Amide,
Mm-hmm. Amide, correct?
the in the middle
Yeah.
one. Yeah.
Yep. Mm-hmm.
And
Nice.
what's COOH? C
Yeah.
double O
So
H.
OOH or COOH, that's often abbreviated as this structure here. So, um, let me draw up here. Where is it? This one here, right? COOH. If I were to highlight that in pink, for example, that's this
Uh-huh.
COOH right here, right? This is the
Um,
COOH.
gotcha. Carboxylic acid.
Yes, nice. Carboxylic acid right here.
Yeah, carboxylic acid, and then um, a amide. The
So this right here is the
uh,
amide.
no, the amine with an N. This corner, isn't it? The left corner.
This N or this over here.
This, yeah, that one.
Oh, so this is an O, right? Um,
Yeah.
and if it's an O, you would think ether, but it's not only an ether because this O R is next to a carbonyl, a carbon double bond oxygen. So this entire functional group is called a
Ester.
ester. Yes, ester.
Ester. Yes.
Ester. Nice. Um, Now we could be more specific with the amide because I just looked at the key, right? Um, if you look at this nitrogen over here, how many carbons is it attached to?
One.
Yeah, one. So we call this a primary amide. This
Um,
condition here will be attached to two
second,
secondary,
second,
right? And this is three
tertiary.
tertiary, right? So if we go back over here, is this a primary, secondary, or tertiary amide?
That's a secondary.
Secondary amide because that
Yeah.
nitrogen is attached to two R groups. Nice.
Yes.
Okay. Yeah. Now let's work with this one over here.
Okay. Two benzene rings straight away.
hmm
Um, carboxylic acid.
hmm Carboxylic acid, correct?
Um,
Nice.
let's see what else is here. Amine, that nitrogen ring.
Correct. And nitrogen attached to this carbonyl, what specific amide is it? Primary, secondary, or tertiary?
Ah, that's secondary.
So this nitrogen here, how many other
No,
carb?
no, it's tertiary. There's three.
Yes, tertiary. Nice.
Yes.
Tertiary
Yeah.
amide. Nice. Okay.
Um,
And then that is it based on what we talked about. But let me check the key if this is something because this right here is technically a functional group, but we call this an aromatic. Aromatic. Have you learned about aromatics yet? Aromatic, non-aromatic, and anti-aromatic?
no, I've heard about aromatic, but I thought aromatic and the benzenes are just the same.
Yeah, so benzene is an aromatic, but aromatic is a bigger term because it includes more things than benzene, just like this
Um,
structure here. This structure is also aromatic. Right?
um,
But let me check the key if they include that. If not, then we don't have to worry about that.
okay.
Yeah. Let me see here. Yeah. So here, we have a phenyl group, which is aromatic ring, secondary amide, ester, carboxylic acid, tertiary amide, phenyl aromatic ring, and this is also aromatic ring as well.
Why is the benzene called phenol? Why
Yeah.
don't we just call it benzene?
Yeah, I think it's because there's two benzenes attached together by one bond, like this. Like one benzene here, another benzene
Oh,
here, and then together it's called phenol, right?
okay.
And if it was just one benzene, then we would call that benzene. But because they highlighted both benzenes attached together by one bond, they call that phenol.
Okay.
Mhm.
Gotcha.
Nice. Okay. And
Mm.
then we call this here aromatic, but specifically it's a tetrazole ring. Tetrazole ring.
What made it tetracycline? Is it because of a lot of nitrogen?
Yep, a lot of nitrogens, and two double bonds and one pair of electrons that can do resonance with each other, like that, right?
Tetracycline because of the nitrogen. Okay.
hmm So tetrazole, like this here, is not very common functional group, not common functional group, right? But it is an aromatic, right? That's the common thing about it. That this is an aromatic here.
Um,
hmm
perfect.
Yeah.
If I get a question in the exam and I just write aromatic, but not say if it's tetrazole or benzene, is that wrong?
Yeah, no, that wouldn't be wrong. That would be correct. Like it is considered an aromatic.
Okay.
hmm Yeah, so an aromatic is like a ring with a lot of double bonds.
Okay.
hmm Nice. Okay. So now let's move on to the next part of question one here. Indicate whether each of the functional group in both molecules is acidic, basic, or neutral. Okay. So let me show you the definition. Well, there's different definitions of acids, base, and neutral, but I
Mm-hmm.
think they're talking about Bronsted-Lowry uh Lowry definitions,
Mm-hmm.
right? So that means that the acid is going to be the ones that would donate a proton, right? A H plus ion, a hydrogen.
Okay.
A base will accept a proton, an H plus ion, right? So some
Yep.
examples here of, let's say, different acids, base, and something that's neutral would be something like this, right? So an example of an acid would be carboxylic acid, where the acidic proton that can be donated is this hydrogen here of the carboxylic acid.
How do we know that the hydrogen can be donated?
Yeah. Have you learned about resonance yet, Sharon?
No,
No. Okay.
not.
So, what resonance is the movement of electrons. So
Mm-hmm.
basically, if we have this carboxylic acid over here, do you know how many
Yep.
invisible pairs of electrons are on this oxygen and how many invisible pairs of electrons are on this oxygen over here?
Like four?
Mhm. Yeah, there's gonna be four electrons, right? And that would be two
Yeah.
pairs, right? One pair here, two pair there. One pair here, two pair there. Right? Now let's say we have a base like hydroxide ion with a negative charge. This oxygen here would have three pairs of electrons or six lone electrons like this. One, two, three, like that. Right?
Mhm.
Now in this reaction here, we will consider this the acid and we will consider this the base. Right? And when we draw arrows in organic chemistry, right, like this, that represents the movement of two electrons. So when you see an arrow like this anywhere in organic chemistry, that represents where the electrons, the two electrons, are moving to, right?
Okay. Yep.
So, what partial charge does this hydrogen have over here? Partial positive or partial negative?
Positive.
Yep, correct. Because that hydrogen there is attached to an electronegative oxygen atom, making that hydrogen partial
Uh-huh.
positive, and this oxygen partial
Yep.
negative. Now, is this negative charge attracted to this positive charge or attracted to this negative charge?
Attracted to the negative charge because it's already positive.
Uh-huh. Yeah, so opposite charges attract, right?
Yeah.
So this negative charge here is going to be attracted to this positive charge over here, right?
Oh,
Because w one of the pairs of electrons, let's say that one, it doesn't matter which one, will go in and grab that proton right there in an acid-base reaction. Like this oxygen here will
um,
make a neo bond with this hydrogen because you know how every bond here represents two electrons? Like there's two electrons here,
yes.
two electrons here, two electrons here,
Yes.
electrons here. This oxygen here is trying to make a bond with this positive charged hydrogen with these two electrons right here.
So they're basically sharing those electrons.
Yes, yes, they're going to share those electrons. But hydrogen
Um,
would not be happy if we don't do anything else because hydrogen does not want to have two bonds. Like if we make a new bond there, that would be a very unstable hydrogen right there.
okay.
So what we would have to do now is look at the two electrons on this bond right here and move those two
Mm-hmm.
electrons on that bond onto the oxygen like that.
So they can get the new electrons from the other side.
Right. So that's why that oxygen there will have three pairs of electrons in a negative charge. And this O minus here will become water, H2O,
Mm-hmm.
like that. Because this oxygen here previously had only one bond to hydrogen, but now it has two bonds to hydrogen because it grabbed this hydrogen over here.
Yes.
And it grabbed it using one of its pairs of electrons, which is why now we see that this neutral oxygen has two pairs of electrons, like that,
Okay.
right?
Makes
And
sense. Yep.
if you look at this oxygen over here, right?
Yeah.
Before this oxygen had two pairs of electrons. Now it has three pairs of electrons because it gained another two from this bond here. The two electrons on this bond went onto the oxygen, giving that oxygen a pair of electrons and a negative charge. Like that.
Oh,
hmm
so if it's negative charge, it's called base, right?
Yeah, and
It's a
this is
base.
specifically a conjugate base.
Oh, conjugate. What's the definition between conjugate? Do you just say with the base? It's like a
Yeah,
part of
the
the name?
definition. of conjugate is that it comes from the acid, right? Because this molecule here
Oh,
came from the acid, so this is the conjugate base of this acid right here, right?
oh, okay.
We would then call this the conjugate acid,
Okay, makes sense.
right? Because this conjugate acid came from this base right here.
Hmm.
Mhm. Right. Now, have you heard of the definition of strong acids lead to weak conjugate bases?
No.
Mhm. So that is going to be a common term that you're going to hear. Strong acids will make or lead to weak conjugate bases, right? So what that means is that if you look at this conjugate base over here,
Yep,
see how here there's three pairs of electrons on this oxygen right here.
yep,
We can move one of the pairs of electrons down to make a double bond between this carbon and this oxygen right here. But you know the
um,
octet rule, how the carbon only wants to have four bonds to be neutral and happy?
yeah.
That would break the octet rule if we don't do anything else, right? Because this carbon would then have one, two, three, four, five bonds if we make a new bond, double bond right there, right?
Okay.
So
Yep,
to conserve the octet rule, to save the octet rule, we could move two electrons of this bond right here onto the oxygen like that, right? So the two electrons here on this
yeah,
oxygen is going to go down to make a double bond between this carbon atom and this oxygen atom, which will then
yep.
move the two electrons on this bond onto the oxygen like that,
Oh, okay.
right?
Because either ways, we have to have four bonds, not five.
Yes,
That's why, okay.
right, on the carbon. Right. So that would lead us to this resonance structure over here, like that. After we
Okay,
draw
yep.
those arrows, right? Because we now have a double bond right here and a oxygen that is negatively charged with an extra pair of electrons like that, right there,
Mm-hmm.
right? And all resonance structures will have the same overall charge. The overall charge of this molecule is -1. The overall charge of this molecule is also -1. It's the exact same,
Yep,
right?
yep. We just
And
rearranged it.
yeah, we just rearranged it. Like the electrons here are moving in time. Like this structure here that you see is one snapshot in time, but they're
Hmm.
actually like in real time moving in between these three atoms right here. They're flowing in between these three atoms right here. So if you were to draw this structure here like this, the electrons are actually flowing in between the oxygen atom here and the carbon atom over there, like that.
Okay.
They're constantly flowing dynamically between these three atoms. But this is just one snapshot in time. This is another snapshot in time, like that. Right? So that's why we call this to be delocalized, right? Meaning that the electrons are not stuck, they're delocalized, they're able to do resonance, and that makes it more stable. That makes the molecule more stable, right?
Mm.
And if the molecule is more stable and happy, it would be less reactive. And if it's less reactive, it would be a weaker base or weaker nucleophile, right? So, which is why this carboxylic acid here is a strong acid because it leads to a stable conjugate base that can do resonance, that's delocalized, right? And because
Oh,
it's so stable, it's delocalized, we call that a weak base.
do we have a strong base or is it always a weak base?
Yeah, so if we try to make a strong conjugate base, that would come from a weak acid, right? So if we were to then, let's say, look at water, for example, which is a weak acid, H2O, and we were to then let's say use a strong base like NH2 minus to try to grab that hydrogen, make a new bond between the hydrogen and nitrogen,
Hmm.
making the two electrons on this bond between the hydrogen and oxygen go into the oxygen. That would lead to these molecules, right? where we see that in the left side, this H2O was the acid because it donated a proton. This NH2 minus here is the base because it accepted a proton. It went to make a new bond with that proton. Now, can you tell me which one's the conjugate base and which one's the conjugate acid in the right side, in the product side here?
This one is the conjugate base, the one that's on the left hand side.
Yeah, so this right here is the conjugate base because it
Yep.
came from acid,
Yep.
right? And the NH3 here would be the conjugate acid because it came from the
It's
base,
yep.
right? Now, if you look at the conjugate base of this OH minus right here, can this negative charge do resonance? Can it move anywhere to move another like pair of electrons anywhere? Like, can it do this or no?
It can.
Right.
They
So,
can go around.
in this case, it cannot because like you know how hydrogen here does not want to have two bonds,
Yes.
right? We don't want that to happen, so it cannot do that.
Oh,
And
how?
there's nothing else to kick out. But in the previous case right here, we were able to make a double bond between this carbon and oxygen because we were able to fix the mistake immediately by moving the two electrons
Oh,
on that bond onto the oxygen right away.
oh,
Hmm. Right. But
okay.
there's no like other pair of electrons or double bond or carbocation to do resonance with here, right?
Mm.
So
Okay, makes sense. Yeah.
the electrons here are going to be stuck. They're going to be localized. And if they're localized, they're going to be very unstable, right? Unstable. And
Um,
because they're unstable, they're going to be reactive. And because they're reactive, they're going to be considered a strong conjugate base, right?
okay.
Hmm. And if it's a strong conjugate base, that means that it came from a weak acid, like that.
Um, so as long as for the conjugate base, as long as the um hydrogens or not oxygens can move around and be called delocalized, they're stable and less reactive, and they're
Yeah.
called weaker bases.
Yeah, like as
Ah,
long as the conjugate base is able to do resonance by being delocalized, moving around, it's like at least three atoms, they're gonna be like stable, happy, and because if they're stable and happy, they're gonna be less reactive, weak conjugate base,
mm,
right? If they're not able to do delocalization, if they're localized, if they're stuck, that would make them very angry, very sad,
and
very unstable, making them more reactive, wanting to react with something, making that a strong conjugate base.
that
And if
makes so much sense. Yeah.
Mhm, that's good. And that means it wants to go back to this form that it was before, that was more happy. That's why this is a weak acid because it does not want to get to this unstable form. It does not want to donate its proton because that would lead to a unstable molecule. That's why this is a weak
Um,
acid, right? And that's why this is a strong acid because it is like it doesn't mind. It can tolerate this hydrogen leaving because it can lead to a product or that is stable. That's why this is a strong acid,
okay.
right? And
And
that's why yeah.
one more question.
Yeah.
How would you know this? Like if you were to look at a structure or a formula, how can you know this? How can you know that if
Hmm.
hydrogen or oxygen needs to move or not? You know what I
Hmm.
mean? Like if you
Yeah,
give
like
me
resonance,
this
like
structure, I wouldn't know.
right? So let me show you here of different things. If we look at, let's say, a carbonyl example, an alkene example, a carbocation example, um, even multiple alkenes in a ring, like that. right? So you know how arrows represent the movement of two electrons, right? Like this represents the movement of two electrons. The base of
Yep.
the arrow here tends to be the electron source. Like there's electrons that start here, and then where do you think the electrons will go towards to? What charge do you think the electrons will go towards to? A positive charge or a negative charge?
Positive.
Yep, positive charge, right? Because
Yep.
um electrons are negatively charged, which will attack positive charge. So keep that in mind in organic chemistry. That's always the case. The negative charge will always go towards the positive charge, like that,
Mm,
right?
okay.
So now, if we go over here, where do you think we are going to start our arrow from? Will we start our arrow from here or here to draw the resin structure smoothly here? Like, where's the biggest
Mm,
negative charge you see?
from the double bond?
So there are negative charges there on the double bond. But we see a clear negative charge here on this carbon here, which is this pair of electrons right there,
Yeah.
right? So, what we could do here is this, where do you want to move the pair of electrons on the left side, or do you want to move it on the right side like that to make a double bond in between these atoms? What makes more
I
sense?
think it's I think it's more stable if it's on the right hand side.
Yep, it would be more stable because to save the octet rule, we can move two electrons of one of the bonds here onto the oxygen like that.
On top of them.
Right. And here's another tip. What is the hybridization of this carbon here? Is it sp, sp2, or sp3 hybridized?
Um, I'm not too sure about that one.
Yeah, so hybridization is talking about like how many bonding groups are attached to an atom. So let's say for example we have an alkene and an alkyne like this. And we're gonna
Yes,
focus on these blue carbons right here, right? So how many bonds do you see on this carbon here?
two.
Yeah, we see two explicitly, but how many carb bonds does carbon want to have to be neutral? Right? It wants to
Three.
have four bonds to be neutral, the octet rule,
Oh yes, no, no, yes, 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 yes.
right?
Four bonds,
And
yeah.
we only see two here, so there's two invisible ones. What invisible bonds, what groups are they attached to here? What atom here?
Hydrogens.
Correct, hydrogen. So there will be two hydrogens on this carbon here. So how many bonding groups? Bonding groups is going to be considered a
Four.
single bond, a double bond, a triple bond, even a pair of electrons like that. Correct? There's four. One, two, three, four. Right? Now, if there's four bonding groups, we call that atom sp3 hybridized. If there's three bonding groups, we call that atom sp2 hybridized. If there's two bonding groups, we call that atom sp hybridized. Right? And that would mean that they have zero unhybridized p orbitals for sp3, one unhybridized p orbital for sp2, or two unhybridized p orbitals for sp. So let me make this make more sense. So in general chemistry, when we talk about electrons over here, there's going to be four orbitals, s, p, p, and p, right?
Yes.
Um, if all four are hybridized together, right? One, two, three, four, they would form an sp3 hybridized orbital.
Uh-huh.
Right. Now, if only three of them form together, they would form three sp2 hybridized orbital and one unhybridized p orbital because this one over here did not mix together with these three orbitals to create the sp2 orbital.
Okay.
Right. Now, how about two? How many sp orbitals would form here? How many orbitals does it take
Only
to
one.
so one s and one p come together? total, that would
True,
be
true,
right.
true,
And how many unhybridized orbitals are there? Unhybridized that did not combine together.
true.
Yeah, two. So that would make it two unhybridized p orbitals like that, right? And it will take all four orbitals to form sp3, right? S and then three p's, right? So that means there will be zero
Uh-huh, yes.
orbitals like that.
Okay, makes sense.
Mhm. Right. Now, because you said there's four bonding groups here, what
Yes,
is the hybridization of this carbon here? Is it sp3, sp2, or sp hybridized?
SP3.
Yep, correct. sp3 hybridized.
Yep,
Now, how about this carbon over here?
that's also SP3.
Huh? So, how many invisible hydrogen bonds do you see on this carbon?
Two more,
Huh? So, how many bonds do you see right now on that carbon, like explicitly, with no invisible bonds?
three bonds.
Mhm. Three. One, two, three. And how many? What
Yep,
was the rule that we said that carbon
four.
needs four? So we already see three.
Yes,
How many are missing?
two more,
So
which makes it one.
four minus three, one, one. So
Yeah,
only one invisible hydrogen,
yep.
right? So that would be three bonding groups. One, two, three. That's three bonding groups.
Oh, so
Because
this
these
double
bonding,
bond you counted as one.
yeah, you count the double bond as one, you count triple bond as one, you count a pair of electrons as one, you count a single bond as one.
Ah, okay.
Mhm.
That's
Nice.
gonna be three sp2.
Yes, this carbon here is sp2 hybridized. Nice. How about this carbon over here? Is this carbon sp3, sp2, or sp hybridized?
I think it's sp
Huh? Correct. Because there are two
since the
bonding groups. One,
yes.
are there any invisible hydrogen bonds anywhere on this carbon or no?
Uh, I don't think so.
Yeah.
No.
No, correct. Because this carbon here already has its octet rule fulfilled. One,
Yeah.
two, three, four. Four bonds,
Yep.
the electrons. Okay, nice. Okay, so if we go back to here, right? And I ask you again, what is the hybridization of this carbon here?
SP4. No, no. SP1. That's SP2.
Hmm? Correct, sp2. Nice.
Yep.
Got it. You're getting it, Sharon.
Yeah.
Yes.
Finally.
Right? Because how many bonding groups do you see on that carbon?
Two. No, three. One,
Three.
two, three.
Right.
Three.
One, two, three. Nice. Zero
Yep.
invisible hydrogen. Now, if you take a look at this pink carbon over here, what is the hybridization of this pink carbon over here?
Mm, SP3
Yes,
because there's
sp3.
two visible and two invisible.
Two invisible hydrogens or three invisible hydrogens on this pink carbon?
Three, actually, three because there's one already there.
Yep, one, and that means there's three missing. One, two, three hydrogens like that,
Yep.
invisible. So there's four bonding groups here. One, two, three, four, making this carbon sp3, right? So notice how this negative charge here is going towards the sp2 carbon, not the sp3 carbon,
Yes.
right? So that's the thing I wanted to get at here.
Mm,
sp3 carbons or atoms are roadblocks to resonance, roadblocks to delocalization, to
uh-huh.
resonance. You can't move electrons to sp3 atoms, but you can move electrons to sp2 atoms, like this, right? And if I were to draw out the resonance structure as a result, we are going to get this resonance structure over here, where oxygen has two pairs of electrons. Now it has three pairs of electrons because it gained this extra pair of electrons from this bond right here. This pair of electrons here created this double bond right there, like that. And we have to make sure that the charge overall is maintained. The overall charge of this molecule is -1. The overall charge of this molecule is also -1.
Mm-hmm.
So they are correct resin structures of each other. So if we were to draw out the hybrid resin structure, it would look like this, where the electrons are delocalized around these three atoms in real time. They're flowing in between those three atoms, right? Like if you take a picture at one point in time, you could see this, or you could see
Yep.
this right here. Nice. Nice.
Uh-huh.
Hmm. Any questions on that, Sharon?
No, that one's fine.
Let's get let's move on to this one here. How would you draw the resonance arrows for this structure?
Um, can we move these two hydrogens and make a double bond on the right hand side?
Yes, not the hydrogens, but the pair of electrons.
Oh, the electrons, yeah.
The electrons are going to make a double bond right here between this atom and this atom like
Yep,
that. Nice. Now,
yep.
do we stop there or do we draw another arrow somewhere?
We need to draw an arrow somewhere else, but I don't know where.
Mhm.
If we move this here,
Yep.
can
So,
we
huh? Okay.
can we move this top part to the
Uh-huh.
bottom?
At the bottom, like right here.
On the right, yes.
Yeah. So, what is the hybridization of this carbon over here again, Sharon?
This one.
Hmm.
It's missing three, so let me see. S SP2.
Hmm. sp3. And did we say earlier that can we move electrons towards sp3 atoms or no?
Oh no, you can't.
Yeah,
No, you
because
can.
we cannot,
Oh no, we
right?
cannot. Okay, yeah, yeah.
Yeah. And the reason why is because let's say you did try to do that, make a double bond right there, you can't move these bonds anywhere else.
Oh, they're gonna be stuck there.
They're stuck there, right? And that would this carbon dioxide would then have one, two, three, four, five bonds. That's not good,
Oh,
right? We can't do it here as well because this carbon is also sp3, right? But what we can do is that we can move these two electrons onto this carbon here itself, right? And when we do
yeah,
that, we're gonna get this resonance structure over here, where now this carbon here is now neutral. There's no negative charge, but this carbon over here that has a pair of electrons is now negatively charged, right? Because this pair of electrons here in purple came from that bond. This pair of electrons here made that double bond right there.
okay,
Just
yeah.
right. Any questions
And
on that one, Sharon?
mm, nope.
That's good. Okay. Now let's take a look at this one over here. Now, are you familiar with formal charges, Sharon? Like how to know when a carbon is supposed to be negatively charged and how to know when a carbon is supposed to be positively charged and how to know when a carbon is like neutral or any other atom like oxygen, nitrogen, bromine, chlorine.
Mm, uh, I know like some of them, but most of them I don't know.
Mhm. Yeah. So if you look at the periodic table, you know how carbon would be
Yeah,
on group 4A on the
yep,
periodic table. If the atom
yeah,
is on that group or like whatever group it is, that means that that carbon must have four electrons to itself, right? So if we take like let's say a look at this carbon over here on pink,
yeah,
right? That's a neutral carbon because you know how each bond here has two electrons, right? That are shared between two atoms. Like let's look at this pair of electrons over here. Let's say one electron belongs to the pink carbon and the other electron belongs to the hydrogen. So that means that this carbon here will have one, two, three. four electrons to itself. Does that make sense so far?
Yes.
So that's gonna be, let's say how many electrons it has. It wants, I mean, it wants to have four electrons because it's on the fourth group, minus how many it has right now. Minus four. Four minus four is
0.
zero. That's why that carbon is going to be neutral. Now, if I were to give you this carbon over here, we know that this pink carbon here wants to have four electrons because it's on the fourth group of the periodic table. But how many electrons do you see it has to itself?
3.
One, two, three, four, five electrons to itself.
Oh, I forgot the single ones.
The single electrons belong to the carbon all to itself,
Ah, okay. But
right?
that's too much.
Four minus five is
1.
negative
-1.
minus one, which is why that carbon there with the pair of electrons is going to be negatively
And
charged.
aha,
Like that, right? Now, if we look at this pink carbon over here with no invisible hydrogens, or yeah, I drew out all the invisible hydrogens already. There's only one invisible hydrogen. There's no two invisible hydrogens. How many electrons do you see that this carbon has to itself right here?
3.
Three, right? One,
Yeah,
two, three. Four minus three
that's
is
gonna be a positive
yeah, positive
charge.
charge, right? Positively charged carbon like that. And a positively charged carbon, we call that a carbocation, like that. But a carbon
Carbocation
and then a cation is something that's positively charged. So this is what we call a
and
carbo.
anion.
Anion is negatively charged. Like up here,
Yep, anions.
it's going to be a carb because it's a carbon. Carb and ion, right? Carb anion is negatively charged carbon. Nice. Okay. So if you go over here, and this carbon we see is positively charged, how many invisible hydrogens are attached to this carbon here?
2 more. It already has 2.
Yeah, it already has two, but if it has two more hydrogens, this carbon would not be positively charged. It would be neutral because it would have four bond electrons to itself. One, two, three, four. So
Yeah.
it would not have two invisible hydrogens because it has a positive charge, right? So here's the trip. We know that that's a carbon, so it was four electrons, and we don't know. Let's say how many electrons it has to itself. Four minus x
Yeah.
equals positive one because we do see the charge on that carbon right there, right?
Mm-hmm.
Let's solve for x here. Right?
Is that
4
3 then?
equals x, and then x equals 3. Right. So we know that
Um,
carbon must have three electrons to itself, right? We already see two here, one, two. It's missing one. So that missing one is only the this invisible hydrogen over here. So this carbon here only has one invisible hydrogen, not two.
okay.
Right? And the reason why we know it's only one and not two is because of this positive charge over here. Right? If there was no positive charge over there and this carbon was neutral, then you would be right. There would be two invisible hydrogens like that, which would make it neutral.
Mm,
Like four minus four, one, two, three, four, zero. But because we see a positive charge right there, this carbon will only have three electrons to itself, meaning that that carbon will only have one invisible hydrogen like that.
mhm.
Okay, nice. Now, it does not fulfill the octet rule because it's missing two electrons, right? It only has six electrons, two, four, six. It's missing a bond. It's missing two electrons.
Yeah.
We can move this pair of electrons down to make a double bond right there, which will give us this resonance structure over here, like that. Right? Where this yellow pair of electrons right here made this double bond
Yeah.
like that. And that
Yes.
because the overall charge is zero, overall charge is zero, it matches, so that's good.
Okay.
Yeah. So I hope this session helps, Sharon. I will send you the notes of the
Thank
session
you.
email right away and the
Thank you
uh,
so much.
thing as well, Sharon. Of course, no worries.
Thank you. Enjoy
Yeah,
your night.
you too. Good luck
Thank
on your
you.
exam, your school.
Thank you.
Bye bye.
Yeah.